My name is Mark Madison, and I'm here with Terry Wong. We are fourth-year chemistry majors at Cal Poly San Luis Obispo. And today, we're going to talk to you about calculating entropy changes in a system. So we want to know what the standard change in entropy is when 1 mole of ethane gas combusts. We also want to know, from the value we get, is this reaction spontaneous or not? So our reaction here is we have 1 mole of ethane, C2H6, plus 7/2 moles of oxygen, makes 2 moles of carbon dioxide, and 3 moles of water. We're given the standard entropies in this table right here in units of joules per mole Kelvin. The way that we calculate the change in entropy, that's delta S, is it's the sum of the products minus the sum of the entropy of the reactants, with this N right here being the stoichiometric coefficients up in our reaction. So let's go ahead and add these values in. We have that our delta S is equal to 2 times 213 joules per mole Kelvin. That's for our carbon dioxide. We have 3 times 188 joules per mole Kelvin. That's our water. That is subtracted from 1 times 229 joules per mole Kelvin. That's our ethane. Plus 3.5, that's 7/2, times 205 joules per mole Kelvin. So when we add these values together, for the product side, we get 990 joules per mole Kelvin minus 946.5 joules per mole Kelvin. Now when we combine these two, we have that our delta S is equal to 43.5 joules per mole Kelvin. That's positive 43.5 joules per mole Kelvin. Now, is this reaction spontaneous or not? So let's talk about the second law of thermodynamics. Second law of thermodynamics tells us that in an isolated system, natural processes are spontaneous when they lead to an increase in disorder or entropy. So our entropy value, if you remember, delta S, was positive 43.5 joules per mole Kelvin. The fact that the change is positive means that it had an overall increase in the entropy of our system, meaning this reaction is spontaneous. So there's another way that we can figure this out too, just based off the number of particles that we have in our system. Now these are all in the gas phase. Let's keep that in mind. Particles in the gas phase are in a state of constant motion, so they're pretty disordered in and of themselves. But let's look at what we start with. At the beginning of the reaction, we start with 1 plus 3.5 particles, which gives us 4.5 particles on the reactant side. And at the end of the reaction, we have 2 plus 3 particles, which gives us 5 particles. So nature is always going to favor turning a lesser amount of particles into a greater amount of particles, because that leads to more possible orientations and just more disorder in the system. So just judged off this, we can also determine that this reaction is in fact spontaneous. So a really quick recap of this whole thing. The change in entropy is calculated by subtracting the sum of the entropy of the products from the sum of the entropies of the reactants. We determined that the change in entropy was positive. Therefore, by the second law of thermodynamics, this reaction is spontaneous. Also, we started with less particles than we ended with, which again also indicates that this reaction is, in fact, spontaneous.